Okay, so welcome back to part 2. So we have already covered all of this, and now we're going to be moving on to this. So if you've made it here, I'm assuming you've already got your PDF download ready to go, but if not, head back to the part 1 where you'll find out where to find it. It's in the description. Alright, so let's get going. Okay, so now on to main energy levels. So the main energy levels are made up of the sublevels. So there are 4 sublevels. We've got S, P, D, and F. And they all have different energies, as we're going to see in a bit. And yeah, these are then broken down into orbitals, and yet each orbital can hold 2 electrons. Again, we'll look at that in more detail in a bit. So let's kind of see how this works. So kind of converting what we know already about the shells, and then kind of applying the sublevels to this. So let's have our little nucleus here. Oh, let's use a pen. So we've got our nucleus. This will be N1, N2, and N3. So just, yeah, building on what we've just done now. So N1 can only have 2 electrons in it. So N equals 1, 2 electrons. And these 2 electrons are in the 1s subshell. Now, up to N equals 2, that's a total of 8 electrons. So 1, 2, 4, 5, 6, 7, 8. And these 8 electrons live in the 2s orbital, and the 2p orbitals. And then finally, N equals 3, so this can hold a total of 18 electrons, so I'm not going to draw them all in, but yeah, these live in the 3s, 3p, and 3d subshells. And we're going to find out more about these subshells and orbitals right now. But before we do that, we need to know the shape of some orbitals. So yeah, all you need to know is the shape of the s orbital. So here are the s orbitals. So the s orbital is basically just a sphere. And then yeah, the spheres get bigger as you move up in principal quantum numbers. So yeah, so the 1s orbital is the smallest. And then yeah, it goes all the way up to 7, so that will be the biggest. But yeah, here we can see the 3s, it's just a bigger sphere. Now we have 3p orbitals, so this is really important. So we've only got one type of s orbital, so there's only one s orbital. And then the p orbital, so there's 3 different p orbitals. And there's px, py, and pz. So px, so this is the shape of the orbital, it's like this 2 lobes. So the px orbital is on the x-axis, py is on the y-axis, and then pz is on the z-axis. So yeah, so if we said that these were like 2p's, a 3p orbital would just be a bigger version, not that big, but you get the idea, it would just be a bigger version, but the same shape of what we've got here. Okay, but yeah, the really key thing is to remember is yeah, that each orbital can only hold 2 electrons. And yeah, these are the shapes you need to know. So just the s orbital is a sphere, and then the p orbitals are these 2 lobes in the different directions on the 3d axis. Okay, so now everything's going to come together now, I hope. So if you're struggling a bit at the moment, that's okay. But now, in our final point for today's video, everything's going to come together and tie up neatly, I hope. So yeah, so orbitals can hold up to 2 electrons, as we've been talking about, and yet each sublevel has a fixed number of orbitals. So again, these are things we've been talking about, but now everything's going to hopefully come together. So yeah, so each orbital has a defined energy, and it can hold up to 2 electrons of opposite spin. And yeah, an orbital is a region of space where there is a high probability of finding an electron. So a little orbital definition for you there. And yeah, this is kind of what it looks like in terms of our energy diagram. So now we've got our sublevels. So we've got our sublevels, and then we've also got our orbital. So each box is representing an orbital. So we know we've only got one type of s orbital, and then the other three types of p orbitals. So hopefully things are coming together now. So yeah, so looking at this diagram, we can start to build up more of an idea of the electronic configurations of the different atoms. So to put simply, this is where the electrons live. So from the diagram, we can see that the one s orbital, has the lowest energy, and then we only need to know up to 4p. So 4p has the highest energy because it's at the top of this graph. So yeah, hopefully you can also notice that the orbitals are getting closer in energy as we go higher up. So yeah, this is the biggest gap here. So yeah, so as the principal quantum numbers increase, so n1 is the lowest energy, and yeah, it goes all the way up to n7. So the shells, the principal quantum numbers, are getting closer in energy. And in some cases, this is going to give us some overlap. So yeah, so some levels are actually lower in energy than you would expect. So we're going to look at this in more detail in a bit, but yeah, we can hopefully, well, we can maybe see that, yeah, so the 4s is actually at a slightly lower energy than the 3d. So yeah, so what you know is, yeah, so that the 4s, so the 4s orbital is lower in energy than the 3d orbital, so it's going to get filled first. But anyway, before we get to that, we're kind of getting ahead of ourselves. So yeah, before we get to all of that, we need to look at how the orbitals are filled. So just as I was hinting at, the electrons always want to be at the lowest possible energy. So on to our analogy for today. So here we have the electron hotel. So it is an upside down pyramid. So electrons love staying in upside down pyramids. So yeah, so we can imagine that each orbital is a room in the hotel. So the electron hotel. So we've got our different rooms. So at the moment we've just got our 1, 2, 3, 4, 5 rooms. But yeah, there's lots of rooms in the electron hotel. And the best rooms in this hotel are always at the lowest energy. And this is our first principle. So there's 3 principles that we're going to go through that you need to know, and this is our first principle. So the Aufbauen principle. So electrons move into the lowest energy orbital as possible. So you always fill from the bottom, basically. So in our electron hotel, the electrons are finding the room closest to the door and are ideally on the ground floor. So that means is that, yeah, so the 1s orbital is going to get filled up first. So yes, we're looking at hydrogen. Hydrogen has 1 electron, and its 1 electron is going to go into the 1s orbital. It's not just going to go crazy and start going into a 2p orbital. We're always filling from the bottom. And then yeah, when those orbitals are full, so when the rooms at that electron of the electron hotel are full, then it has to move on to the next available energy. So if we look at lithium, so lithium has 3 electrons. We've got 2 electrons in here, and then yeah, the 3rd electron has to go in the 2s orbital because the 1s orbital is full. But what happens when we get a choice? So when we have a choice, so now the 2s orbital is full, and the next electron has a choice of where it wants to go. Well, luckily, all the 2p orbitals are the same energy, so this is described as degenerate, so they're the same energy. But yeah, so we've got 1 electron in here already. Clearer. So yeah, so this doesn't really matter if it goes in here or in here, it's okay. Or in here, as these 3 orbitals are the same. But what happens when the next electron comes along? Where is this going to move into in the electron hotel? Well, we need to look at Hund's rule. So orbitals of a sublevel must be filled by single electrons with a parallel spin. So what does that mean? Is they basically don't like to share rooms. So the next electron, so the next electron is going to go here, and then the next electron has to go over here. So what does this mean, spin? So basically, yeah, electrons are tiny little things that are spinning around. So they can either spin one way, or they can spin another way. And yeah, because they have a charge, they basically act like little magnets. So onto our final rule. So when we have all the orbitals filled with their parallel spin, so they're all spinning the same way, then the next electron has to go into an orbital that is already full. But for this to happen, it has to spin in an opposite direction. So once we start filling these orbitals, then the electrons are spinning in an opposite direction. And this is kind of cancelling out the fact that they are negative. So negative things do repel. But because, these two electrons here have opposite spins, then they can kind of cope with each other and they can exist in the same orbital together. So this is Pauli's exclusion principle. So so no two electrons are the same in an atom. So even though they could be in the same orbital or in the same energy level, they are all different because they're either in a different orbital, or even if they're in the same orbital, they have a different spin. Okay, so kind of gone through this now, but let's have a look at some specific examples, and then hopefully this will make it a bit more sense. Okay, so let's start off with a nice and easy one. So let's go for oxygen. So oxygen has 8 positive protons, so therefore it has 8 negative electrons. So where are they going to go? And just so I'm making things zoom in a bit actually. So to make things nice and clear, like this is an electron spinning one way, and then this is an electron spinning the other way. So this is how you have to draw it. You could draw out the full arrows, but you don't need to. So the little arrow is showing that it has a spin. So the first electron going into the lowest energy level, so 1s, and the second one has to go in here, but it has an opposite spin. Same again over here, getting filled like this, and now they fill with parallel spins, and then so that's 1, 2, 3, 4, 5, 6, 7, and then the 8th electron, an opposite spin, but going into the 2p orbital. So we can't use any of these orbitals because these are at a 2 higher energy. Okay, so that's oxygen. Now let's have a look at another example. So let's do magnesium, which has 8. Oh, not 8. That's oxygen. 12 positive protons, so it must have 12 negative electrons. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then 11, 12. Okay, all hopefully quite straightforward, I hope. Alright, but there are 2 special examples that you need to know about that don't quite follow this rule. So let's have a look at what's going on with our 2 special examples. So the first one we're going to look at is chromium, which has 24 electrons. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25. Oh, not 25, 24. Okay, so this is what we would expect. However, this is not what happens. So transition metals have lots of very exciting properties, but basically, electrons always want to be stable. So how are they going to be stable? Well, they can shuffle their electrons around to kind of help out with the stability. So because there's not much difference in energy between the 4s and the 3d orbital, then it doesn't really matter if this happens. So I was only meant to get rid of one. So basically what happens is that this happens. So because none of the electrons are paired up, and also an extra stability is gained from having at least one electron in each d orbital. This is the most stable electronic configuration for chromium. So this is very similar when we look at our next example, which is copper. So copper has 29 electrons. So let's get those filled up. 2, 3, 4, 5, 6, 7, 8, 10, 11, 12, And then, yeah, filling the 4s first. So I didn't say that last time, but yeah, filling the 4s first. This, and then this, and then filling as we go. So this is, yeah, the 29 electrons. But yeah, so what copper does is it moves one 4s electron over to 3d. So then again, this is just to give it some extra stability. Alright, so hopefully we are feeling a bit happier about how everything is filling, but let's write out the shorthand. So when it comes to writing these out, you do need to be able to write out electronic configurations, but you don't need to do these big long diagrams over here. So there is a shorthand, you'll be pleased to hear. So let's have a look at what that looks like. So you're basically just telling everyone where the electrons are living. So for oxygen, its electronic configuration would be 1s2. So yeah, so this 2 is just telling us how many electrons are in the 1s orbital. Then 2s2, and then 2, 2p5. So there we go. So we've got not 5, 2p4. So yeah, we've got 2 electrons, and then yeah, 4 electrons, 4 electrons. Okay, so let's do the same again for magnesium. So 1s2, 2s2, 2p6, and then 3s2. Happy days. And there is one thing we can do to help speed us up, because the noble gases, they have like a fixed electronic configuration. They're not going to change, they don't become ions. So we can do a shorthand. So you can write neon. So this is the closest. So neon has 10 electrons, so that's kind of filling up to, yeah, the 2p. And then we can write 3s2. So this is kind of summarizing all of this for us. So you don't need to write all of it out. So there we go. So that's how we can do that for magnesium. So let's do the same for chromium. So we have here 1s2, 2s2, 2p6, 3s2, 3p6, make some space, 3s2, no, sorry, I've already done that. Then yeah, 4s1, 3d5. So yeah, just making sure that that gets written first. Okay, so again, we can abbreviate all of this up to here, because this is argon. So AR, and then yeah, 4s1, 3d5. Okay, on to our final one. So yeah, 2s2, 2p6, 3s2, 3p6, 4s1, 3d10. So yeah, we can abbreviate all of that again to argon, because that's the same as before. And then yeah, 4s1, 3d10. And then yeah, final thing, just making sure that this gets written first, because it's at the lower energy. Okay, so there we go, quite a lot involved there, but there we are, that's SL Electron stuff done. Thank you as always for watching, and if you want more new IB chemistry content, please do like and subscribe, and if you are desperate for a specific video, then let me know in the comments and I'll see what I can do. And then yeah, final thing, if you are after more chemistry help in the form of tutoring from me, we can speak in real life over an online interactive whiteboard, then check out my website, link in the description. And yeah, that's all from me. Thank you again, and catch you in the next one.